A ball is thrown downward with an initial speed of 20 meters per second on Earth. There are 6 parts to this problem. Part A, make a label diagram, specify the positive direction. Then, make a motion map of the situation. B, what is the acceleration of the ball? C, calculate the displacement during the first 4 seconds. D, calculate the time required to reach a speed of 50 meters per second. E, calculates the time required to fall 300 meters. F, calculate the speed after falling 100 meters. For part A, I'm going to say that my positive direction is upwards, my downward direction is negative. I'm going to be starting off with the motion map on the top right of the screen. The position of the ball is going to be indicated with that blue circle. Attached to the blue circle is a green arrow labeled V0. That is the starting velocity. Because we have an initial downward velocity of 20 meters per second, I already have a downward facing velocity vector. Next to it, I also have another position marker, but this arrow is A0. That is going to be the acceleration at 0 seconds. My motion map is going to show that the object has a lower position at each increment of time. Another thing that I am showing is that my velocity vectors are getting longer and longer and longer. The object speeds up as it moves downwards. However, I am saying right now that the acceleration will remain constant. We're going to answer why in part B. For part B, I'm going to start off by drawing a force diagram for the ball. The only relevant force acting on the ball after it has been thrown and at every instant in time before it strikes the ground is just the force of gravity. We're making the assumption that air resistance is negligible for this type of problem. That leaves just this force, the interaction between the Earth's gravitational field and the object. As such, we can write our sum of the force equation, showing the sum of the forces vertically is just going to equal the force of gravity. We can write the sum of the forces as mass times acceleration by using our understanding of Newton's second law of motion, and we can rewrite force gravity as mass times our gravitational field strength, using our understanding of how we can calculate the force of gravity for an object near the surface of the Earth. Because we have the same mass on both sides of this equal sign, they can cancel out, allowing us to state that the acceleration should be equal to just the gravitational field strength of the Earth, or the gravitational acceleration of an object near the surface of the Earth. That value would be 9.8 meters per square second. This is the acceleration of the ball while it is freely falling downwards. Now, for parts C through F, we're going to be using our kinematic equations to calculate the displacements, the time, and the speed. As such, I'm going to have a table where I'm going to populate all these empty boxes with the values I know and what I'm solving for. Now, this type of problem, while it is only dealing with vertical motion, it is going to be part of an understanding of projectile motion, which is going to involve both horizontal and vertical motion, which is why I have 2 lists for my horizontal and vertical variables. So when I start filling these in, we didn't have any forces on the x-axis horizontally, so the horizontal acceleration should be 0. The vertical acceleration would be 9.8, and because it's accelerating downwards, the direction we're saying is negative, we're making that negative 9.8 meters per square second. Now for the other variables. In the problem, we were told that the initial speed is 20 meters per second, and because the ball was thrown downwards, that means we can say it's going to have the same sign as the sign of our acceleration, also pointing downwards. Now, the other variables. We're not told anything horizontally, so I'm just striking out those boxes. We don't really need them. Now, for the vertical, we don't know what the starting height is going to be, so I'm just going to say it starts off at a reference height of 0. We don't know where it ends up, nor do we end up its final velocity. But the time for part C, we're told, is 4 seconds. We're figuring out the displacement or the change in position. So that means that we're basically figuring out final position minus initial position, or if we define the initial position as 0 like I have, then we're just solving for the final position. The equation that we have that allows us to solve for that is this one. Our final position is equal to our starting position plus our starting vertical velocity times time, plus 1/2 times our vertical acceleration times time squared. I subtract y naught from both sides, so that way I do actually write my left side of my equal sign as though it were a displacement, even though if we are defining our initial position as 0, final position and displacement would be equivalent here. Now that I've got my variable I'm solving for by itself, I plug in the numbers. Our initial vertical velocity is negative 20 meters per second. The time is 4 seconds. The number 1/2 stays the same. The acceleration is negative 9.8 meters per second each second, or negative 9.8 meters per second squared. And then times our 4 seconds of time, that gets squared. Simplifying that down, that means that our change in position is going to be equal to the negative 80 meters plus that negative 78.4 meters when we just solve those two terms separately. Now, for the next part D, we need to calculate the time required to reach a speed of 50 meters per second. Now, my list of horizontal variables stays the same, as does my starting position vertically of 0 meters, my starting velocity vertically of negative 20 meters per second, and my acceleration vertically of negative 9.8 meters per second squared. Now, for this specific problem, though, we don't know the final position, and we're not solving for it. We are told the final speed is 50 meters per second, and we can make the logical assumption that that is going to be negative 50 meters per second because it, too, is moving down. This means that we just need to solve for our time, our last variable there. So I'm going to choose an equation that has the variables I know and the thing I'm solving for. We know the final vertical velocity. We know the vertical acceleration. We're solving for the t time, and we know the starting vertical velocity. I can rearrange it to get time by itself. To do that, I subtract v naught from both sides, and then I divide the acceleration by both sides. Then I can plug in my values. My final velocity is negative 50 meters per second. My starting velocity is negative 20 meters per second, and my acceleration is negative 9.8 meters per second each second. So when I simplify that down, the time required to reach that downward speed of 50 meters per second would be 3.06 seconds. For part E, where we're calculating the time required to fall 300 meters, we still have that same starting vertical position of 0 meters, starting vertical velocity of negative 20 meters per second, and acceleration of negative 9.8 meters per second squared. Here we know the final position is 300 meters below where we started. So if I start off at a reference level of 0, my final position would be negative 300 meters. We don't know the final velocity, nor are we solving for it. What we are solving for is time. So I can go back to that equation we used for part C. However, for this problem, we're actually solving for t, time, rather than delta y, that displacement. So we're going to have to solve it a slightly different way. Now for this one, instead of rearranging to get t by itself, I'm just going to start off by plugging in the values that we know. Then I'm going to add 300 meters to both sides. When I write it like this, 0 equals 300 meters minus 20 meters per second times time, plus the 1/2 times the negative 9.8 meters per second squared times time squared. Trying to solve for time this way will require us to either plug it into a calculator and plot it and look at the two x-intercepts, or we can go with the quadratic formula. Our time would be equal to our negative b term, which in this case would be the negative 20 meters per second, plus or minus the square root of b squared, that negative 20 meters per second squared, minus 4 times a, this 1/2 times negative 9.8 term, times c, that 300 term. All of that over 2a. If you are going to be solving this using the quadratic formula versus using a graphing calculator and graphing it out, it might be beneficial to write down those steps. but the answer going with the quadratic formula approach or with the graphing approach will yield two viable times, one positive and one negative. Now, our time would have to be the positive solution because this would be the amount of time after it was thrown, not before. So this would be the time for this problem would be 6.05 seconds. Now, the last part of this problem is to calculate the speed after falling 100 meters. We still have these same starting variables that we once did. Now our final position is negative 100 meters, 100 meters below where we started. We're solving for that final speed. We're not given the time, nor are we solving for it. So this is the equation that we can use to solve for that final speed. Our final vertical velocity squared is equal to 2 times our vertical acceleration times our vertical displacement plus our starting vertical velocity squared. To get the term we're solving for, that final velocity by itself, we would just take the square root of both sides. At this point, we can plug in our values. And then solving for that will give us plus or minus 48.58 meters per second. If we were to solve for the velocity here, with our frame of reference where we're saying down is negative, this would be negative 48.58 meters per second. However, because part F is asking us to calculate the speed, we'll just go with the positive term, the absolute value of the velocity here.